Welcome back to this next video in which we are discussing the parathyroid glands and vitamin D. Okay, so we've now discussed two of the actions of parathyroid hormone on the kidneys. Namely, we've seen that parathyroid hormone is going to increase calcium resorption from the glomeruli filtrate by the kidneys, and it's also going to decrease phosphate resorption from the glomeruli filtrate by the kidneys. However, there is a third function of parathyroid hormone on the kidneys, and that is to activate in the renal tubular cells of the proximal convoluted tubule the conversion of an inactive form of vitamin D to the active form of vitamin D. And this active form of vitamin D is then going to help parathyroid hormone to bring calcium levels back up in the bloodstream. So in particular, it's going to help parathyroid hormone with its activity at the bone, which we'll go over later. And in fact, it is going to be the thing which acts on the gastrointestinal tract to increase calcium absorption there, and also to increase phosphate absorption there. So parathyroid hormone doesn't actually directly act on the gastrointestinal tract. Instead, it creates vitamin D in an active form, which is called 1,25-dihydroxyvitamin D. We'll go through all of this, which is then going to have actions on the gastrointestinal tract and cause the gastrointestinal tract to increase calcium absorption and increase phosphate absorption. Okay, so we're now going to have diversion then to talk about vitamin D. So the first thing to say about vitamin D is that there are two different molecules which are both counted as vitamin D. And these two different molecules that are both counted as vitamin D, and which both are equivalent as far as the body is concerned, although they do have different structures. So they do an equivalent thing as far as the body is concerned, but they do have different fundamental chemical structures. These are called vitamin D2 and vitamin D3. Okay, so this is the first important concept, that there are these two different forms of vitamin D, vitamin D2 and vitamin D3. Okay, now both vitamin D2 and vitamin D3, they also have other names which are in common use, so I'm going to give you these other names. So vitamin D2 is also called ErgoCalciferol, and vitamin D3 is also called cholecalciferol. And what we're going to start off with is discussing the chemical structures of these two molecules. So I want to show you the chemical structure of ErgoCalciferol and cholecalciferol. Okay, now rather than just putting on the piece of paper the chemical structures straight away of both of these molecules, what I'd like to try and do is motivate or build up to the chemical structures of these two molecules rather than just putting them on a piece of paper. So, in particular, the way we're going to do this is by looking at cholecalciferol, because vitamin D3, cholecalciferol, this is the one that your skin cells are actually capable of synthesizing from a molecule called 7-dehydrocholesterol. Okay, so when people say, go out in the sun, it'll give you vitamin D, you need some vitamin D, this is the one that they're actually talking about, vitamin D3, because in the skin, you are capable of converting a molecule known as 7-dehydrocholesterol into cholecalciferol when your skin is exposed to ultraviolet radiation. Right. ErgoCalciferol, meanwhile, you are not capable of synthesizing that one. If you're going to receive that one, you have to receive it in the diet, mainly from vegetables. Right. However, as I said, both of these are utterly equivalent, so it's not the case that you need both vitamin D2 and vitamin D3. So if you're not getting any vitamin D2 in your diet, as long as you're getting vitamin D3, then that doesn't actually matter, because vitamin D3 will do all of the job of vitamin D2. So as far as the body is concerned, they are utterly equivalent, and that's why we will often just refer to them both as vitamin D. Okay, right, so the way I'm going to show you then the structure of ErgoCalciferol and cholecalciferol is by talking about the synthesis of cholecalciferol from 7-dehydrocholesterol. So to do that, we need to have a look at the structure of 7-dehydrocholesterol, and in order to look at the structure of 7-dehydrocholesterol and understand it, we need to know the structure of cholesterol. to understand the structure of cholesterol, we need to know what a sterile is, and to understand what a sterile is, we need to understand what a steroid is. So I'm going to build up from the foundations. We're going to start by talking about steroids, we'll then talk about sterols, then cholesterol, then 7-dehydrocholesterol, and then up to cholecalciferol, then we'll talk about ErgoCalciferol. Okay, so that's how I'm going to show you the chemical structures of these two molecules. So we'll start off then with the structure of a steroid. So this comes as a surprise to most people when they learn it for the first time. It did come as a surprise to me when I learned it for the first time, that the definition of a steroid is not biological, it's chemical. Okay, I imagine that the definition of a steroid from popular culture's understanding of steroids was a molecule that was defined by its biological activity because it was incredibly powerful and could affect the body in incredibly powerful ways. Okay, whereas in fact steroids are defined on a chemical basis, they're defined on an organic chemical basis, i.e. what is the actual structure of the molecule. And indeed a steroid molecule is one which its structure is based on a certain chemical structure that I'm about to put on a piece of paper in front of you. So what I'm going to do then is now draw out the core steroid structure, the structure that all the other steroids are based upon and contain to some extent. So the core steroid structure then, it consists of 17 carbon atoms with a huge number of hydrogen atoms bound to those carbon atoms. Now I'm going to draw it in the skeletal form, and remember in the skeletal form you don't show carbon atoms, they are shown instead by the corners of the diagram, and you don't show hydrogen atoms coming off carbon atoms. Where there are missing bonds coming off carbon atoms, it's implicitly understood that you understand that hydrogens are coming off those carbon atoms. Okay, so this means that the steroid core structure ends up looking incredibly simple when you draw it in skeletal form, because all the steroid core structure consists of is carbon atoms bound to one another with hydrogen atoms coming off, and for that reason when we draw it in the skeletal way it's going to look incredibly simple. So the carbon atoms are going to be arranged into 4 rings that are linked with one another. So let me now draw this out. So the first ring is a 6-membered ring. Okay, so here is the first ring of the steroid structure. 6 carbons linked to one another to form a hexagon like so. Then we're going to have another ring joined onto this, which is going to be another 6-membered ring here. Then another 6-membered ring is going to be joined onto this one, like so. And then a 5-membered ring joined onto this one. And this is it. That's the picture of the skeletal structure of the core steroid structure. So let me repeat the fact that a steroid molecule is one where the structure is roughly based on this. It might be a large modification away from this. However, it's based on this to some extent. This is the core steroid structure. Okay, and as I say, the reason this looks so simple is because it literally does just consist of carbon atoms linked to carbon atoms with loads of hydrogen atoms coming off. So where we've got missing bonds, so for instance, take this carbon here, you've got 2 missing bonds coming off that carbon. Those 2 missing bonds would be to hydrogen atoms. Now, let me give you a little bit of nomenclature concerning steroid structures, because there are a few pieces of nomenclature that people use to navigate their way around the steroid structure. So firstly, we name all 4 of the rings of a steroid structure with a letter. So this is called ring A, this is called ring B of the steroid structure, this is called ring C, and this is called ring D. Okay? In addition, we generally number all of the carbons in the steroid structure with a certain number so that we can talk about the different carbons in the steroid structure and everyone knows what we mean because we can give the correct number. So this is the way we number up the carbons in a steroid structure. This one right at the top of ring A here, we call that number 1. And then we're just going to go round in a reasonably logical order, okay? Just round basically and continue on up the number system. So we'll go on to 2 here, we'll go on to 3 here, 4 here, and then just continue on. 5 here, 6 here, 7 here, 8 here, 9 here, 10 here, 11 here, 12 here, 13 here, 14 here, 15 here, 16 here, and 17 here. And now hopefully that convinces any skeptics that there are indeed 17 carbons in this structure. Okay, so that's the way that we name up or number up all of the carbons in the core steroid structure. So, to repeat then, a steroid molecule is one which has this core steroid structure to an extent within it, where the structure of the molecule is based on this core steroid structure that is now sitting in front of you. Okay, now, upper step then. We need now to talk about the concept of a sterol, because remember we want to talk about cholesterol, and clearly cholesterol is a sterol. Okay, so sterol. So a sterol is a steroid. It's a whole class just like steroids, and it's a modification of the sterol structure. In particular, what you do is you put an alcohol group onto the steroid structure in a particular position. You put it onto carbon number 3 here. So carbon number 3 of ring A, it has 2 bonds to other carbon atoms, and then the other 2 bonds are going to be to hydrogen atoms. We're going to cut one of those off, so we'll take one of the hydrogens off carbon number 3, and we're going to replace it with an alcohol group. That will now be the core sterol structure, and any molecule that whose structure is based on that will be referred to as a sterol. Okay, so if I just draw this quickly, so I'll just draw a little picture for this. So here is ring A, drawn quite badly, but never mind. Here is ring B, here is ring C, and ring D, like so. And now we're going to have an alcohol group coming off carbon number 3, like so. So that is the skeletal structure for a sterol molecule, or the sterol core structure. So again, sterols are an entire category, an entire class of molecules. Any molecule whose structure is based on this will be called a sterol. So all sterols are steroids, but of course not all steroids are sterols. So that's what is meant by a sterol molecule. Upper step again, let's now talk about a specific example of a sterol molecule, which is cholesterol, a very famous example of a sterol molecule because of its involvement in the pathogenesis of atherosclerosis and therefore cardiovascular disease. Okay, so cholesterol, what then is the structure of cholesterol? So as I say, this is a specific sterol. So this is a molecule with a specific structure now, whereas sterols and steroids are whole classes of molecules. These are the core sterol structure and the core steroid structure, but really when you talk about sterols and steroids, you don't mean these actual molecules, you mean the whole categories. Okay, whereas cholesterol is a specific molecule. So, cholesterol, firstly it is a sterol, so let's start by copying out the sterol structure here. Okay, so once again, here is ring A, here is ring B, here is ring C, and here is ring D, and we'll need the alcohol group coming off carbon number 3 here. And now what we're going to do is we're going to make 3 modifications to it. Firstly, we're going to put a double bond between carbon number 5 and carbon number 6. And by the way, you keep the same numbering of the carbon atoms in sterol molecules as you have in steroid molecules. So this is carbon number 5 and this is carbon number 6. We're going to put a double bond between them. So carbon number 5, it has 3 bonds to other carbon atoms and 1 bond to a hydrogen atom. Carbon number 6 has 2 bonds to other carbon atoms and 2 bonds to hydrogen atoms. We're going to take the hydrogen atom off carbon 5, take a hydrogen atom off carbon 6, and with their free electrons, we'll then bind them together to form a double bond there. So that's number 1 modification we're going to make to create cholesterol. Number 2 modification, we're going to stick 2 methyl groups on. One onto carbon number 10 here, so that's carbon number 10, and one onto carbon number 13 here, so that's carbon number 13. So, both carbon number 10 and carbon number 13 had 3 bonds to other carbon atoms and then 1 bond to a hydrogen atom. We have cut that hydrogen atom off in both cases and replaced it with a methyl group. So that's modification number 2. Modification number 3, we're going to stick a side chain off carbon 17. So carbon 17 has 2 hydrogens coming off it. We're going to cut one of those off and stick a carbon side chain on instead. And this carbon side chain is going to have 8 carbons, and it's going to look nicely symmetrical like so. And it's a little bit of a squeeze to put it on here, but this is it. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons overall in that side chain that we've stuck on. And the way when I said it's nicely symmetrical, I mean the way that there's a line here and the line here, you know, it's reasonably nice and symmetrical, reasonably easy to remember there. Okay, so how do we then name up the carbons now in the cholesterol molecule? Well, for the actual sterile structure, we leave the naming exactly the same. So we get up to carbon 17 here, and now we're going to have to name up these additional carbons here. So we firstly jump to this one here, and we call that carbon number 18, and I'm sorry it's a bit of a squash, but that carbon in the methyl group coming off carbon number 13, that's called carbon number 18. The carbon in the methyl group coming off carbon number 10, that is called carbon number 19. And now to label up these carbons, I'll actually copy it out here. So I'm going to copy this out larger rather than trying to squeeze the numbers in on that small picture. So here is the side chain drawn out larger. So what we're now going to do is just go up in the logical order. So this is the first one off carbon 17. We're going to call that carbon 20. Okay, then this one's going to be carbon 21. Okay, this one carbon 22, this one carbon 23, this one carbon 24, this one carbon 25, this one carbon 26, and this one carbon 27 there. Okay, so that's the numbering up then of the carbons in a cholesterol molecule. Right, one step further now, we're going to go up to 7-dehydrocholesterol now. Okay, so the molecule that is immediately before cholecalciferol in this synthesis pathway that's going to occur in the skin. So 7-dehydrocholesterol. Okay, so hopefully you might be able to start guessing what this is actually going to be. So 7-dehydrocholesterol, all we're going to do is one modification to the cholesterol molecule, and it's going to be to carbon 7. So carbon 7 is here, and as we can see from this picture, it's going to have 2 bonds to carbon atoms, and then 2 bonds to hydrogen atoms. Dehydro, we're going to get rid of a hydrogen. So we're going to take one of the hydrogens off carbon 7, and we're actually also going to take a hydrogen off carbon 8 here. Okay, and we're going to form a double bond between the two. So the structure then of 7-dehydrocholesterol, let's firstly draw out the structure of cholesterol here, so test yourself, see if you can remember it. So here is ring A, here's the alcohol group of carbon number 3, then we've got ring B here, we need a double bond between carbon 5 and carbon 6, we need a methyl group of carbon 10, okay, here is ring C, we need a methyl group of carbon number 13 there, and then here is ring D, and let's now put our side chain up here, this 8 carbon side chain, which is reasonably symmetric like so, and now we're going to modify this by putting in a double bond there between carbon 7 and carbon 8, and this molecule now, this is 7-dehydrocholesterol. So we are now ready to discuss the synthesis of cholecalciferol, so you should be excited, we're about to see the structure of cholecalciferol. So what we're going to have is we're going to have 7-dehydrocholesterol in the skin, and when this is exposed to ultraviolet light, what can happen is a reaction that's going to break one of the bonds here, and a few new bonds are going to form, and we're going to end up with cholecalciferol. So cholecalciferol is actually going to be a structural isomer of 7-dehydrocholesterol. Okay, so in the presence of ultraviolet radiation then, what can happen is this reaction. So the reaction that's going to occur is you're going to break this bond here, this bond between carbon number 10 here and carbon number 9. Okay? What is then going to happen is carbon number 10 is now going to form a bond instead with carbon number 19, I believe. That's the number for this one, yes. Carbon number 19 of this methyl group up here. So it's going to form a double bond with this one. Carbon number 19 is going to therefore have to cleave a bond to one of its hydrogens. So it's going to break a bond with one of its hydrogens to make that double bond with this carbon. That hydrogen that you've released from carbon 19 is then going to bind to carbon number 9 here. Okay, so I'll repeat that because it's quite important that you understand it. So we're going to break this bond here. In fact, I might just draw this on. So we're going to break this bond here. Imagine sending one of the electrons back to this carbon and one back to this carbon. Of course, this isn't an electronic mechanism. This is just to help you understand it. So there are 2 electrons in each covalent bond, 1 from each atom. Imagine sending the electron from this carbon, carbon 10, back to it, and then give the electron from carbon 9 back to carbon 9. up here with our carbon, and I might just actually draw on the hydrogens for now. So here are the free hydrogens coming off this carbon, so I've broken the skeletal structure for the time being. What we're going to do is we're going to break one of the bonds between the carbon and the hydrogen. Okay, we're going to give one electron back to this carbon, one back to the hydrogen. We're then going to form a bond between this carbon, carbon number 19, and carbon number 10 here to create a double bond there. Then what's going to happen is this hydrogen here is going to form a bond with this carbon, carbon number 9 here, because both of them now have free electrons. So now let's actually draw out the structure of what we will end up with, and this thing that we're going to end up with is cholecalciferol. Okay, so here is ring A, once again. Okay, here is the alcohol group coming off carbon number 3. Now we're no longer going to have an intact ring B anymore. Okay, instead what we're going to have is carbon number 10 here is going to be double bound to carbon number 19, and I'll go back to doing my strict skeletal structure so I wouldn't show the carbon there. Then we're going to have this double bond here between carbon 5 and carbon 6. Then we've got carbon 7 and carbon 8 here, and we'll need those double bound to one another. And now we're going to have ring C, or what's left of ring C. Well, ring C is still intact, but what was previously ring C when we had our unbroken steroid structure. And then here is ring D here, like so. We'll have our methyl group there, and we should still have our side chain there, but I'm not going to attempt to put that in because I just don't have space. What can I do? I can sort of put it in and then have it continuing here. Okay, this is the best I can do. So I'll colour code it so that it's obvious that this should continue on to there. Okay, and I believe that is everything. Let me just check that I've got everything. Yes, I believe I do have everything on there. Okay, so this structure now, this is vitamin D3, or you can call it cholecalciferol. And of course it's called cholecalciferol because it is derived in this way from cholesterol. Okay, so you can make cholecalciferol in your skin in this way when 7-dehydrocholesterol is going to be exposed to ultraviolet light. In addition, you can get it in your diet. In particular, you can get it from fortified bread. Eggs are also a good source of cholesterol, things like that. So fortified bread, all the fortified means is that we have actually put cholecalciferol into the bread, okay, to prevent people getting vitamin D deficient. So nowadays, milk and also bread are fortified so that everyone is always getting enough vitamin D. Okay, right. So cholecalciferol, you can get it from eggs, they're a natural source, but you can also get it from fortified products such as bread. Okay, right. Now let's actually talk about the other form of vitamin D, vitamin D2, ErgoCalciferol, and this is the one that you can't synthesize in the skin from 7-dehydrocholesterol. Okay, so we're now going to see how ErgoCalciferol is just a small modification of the cholecalciferol structure, and that's why this works itself into a nice story. So we've built up to cholecalciferol, and now we can just see ErgoCalciferol as a little bit of a modification of cholecalciferol. So all we're going to do is modify this chain up here, and that will now make us ErgoCalciferol. So let me copy out the structure of cholecalciferol, and that will be a good thing to do anyway because of the fact that it's broken up here. And then I'll show you how to modify it into ErgoCalciferol. So I'll make sure I get enough space this time. So here is ring A. Here's the alcohol group coming off carbon number 3. Here is the double bonds to carbon 19 up there. Then we'll have what's left of ring B, the broken ring B, so a double bond there, a double bond there. Then we'll have what was once ring C, okay, and now we'll have ring D here, like so, and then we'll have our methyl group coming off carbon number 13 here, and now let me draw on our side chain here, which has these 8 carbons, like so. Okay, so this, let me just check again that I've got everything. Yes, this is vitamin D3. To turn this into vitamin D2, ErgoCalciferol, what we need to do is modify this side chain up here, and we don't have to make many modifications, just 2. Firstly, we're going to put a double bond in between this carbon, carbon number 22, and this carbon, carbon number 23. Okay, so in between carbon 22 and carbon 23, we're now going to stick a double bond, like so. So both of those had two hydrogens coming off them. We're going to take a hydrogen off each of them and instead bind them together. In addition, off carbon number 24 here, we're going to stick a methyl group. So we're going to take one of the hydrogens that is off carbon 24 off it and instead put a methyl group on there. And that molecule that we now end up with, this is ErgoCalciferol vitamin D2. Now, ErgoCalciferol you cannot make in your skin using ultraviolet light. Instead, what you have to do is you have to get vitamin D2 from your diet, and vitamin D2 is found in very different sources to vitamin D3. Vitamin D3, a natural source of it was eggs. Vitamin D2, the natural source of it is vegetables. You can get ErgoCalciferol vitamin D2 from vegetables. Okay, right, so we'll have a break there, and in the next video what we'll talk about is firstly how vitamin D molecules are actually transported around the body, and then we'll talk about the activation stages, because vitamin D in these forms, vitamin D2 and vitamin D3, it's not actually that active at all. It doesn't really do much. Instead, it has to be activated to more powerful molecules that are going to actually do something, and it's that process that we're going to discuss in the next video.